Hi everyone. So I'm excited to talk to you a little bit today about optimization. This video accompanies lecture 15 on optimization, and this is a full lecture on that subject. So we're going to have three parts to the lecture. The first is a brief introduction to optimization. The second is how to do basic optimization in Excel using Solver, and finally we'll talk about optimization in Python using some of the functions that are available through scipy. So let's dive right in. So first I'm going to talk a little bit in this intro. I'll write some notes here. So the first piece we'll start will be an intro to optimization. Okay, and if you recall, if you're following along, we talked the last time about we've talked the last couple of days about solving nonlinear equations, and we've talked about two ways to solve nonlinear equations, or two different things we've done. Both of them actually relied on one different kind of method, which were iterative fixed point methods. Okay. And we had two methods in particular we talked about. We talked about Picard's method, and we talked about Newton's method. Okay. And these methods, if you recall, we had something like x equals g of x, all right, and we would make an initial guess, and then we would put it here, say x0. We would then calculate g, which would produce x1, and then we would plug that in here, and then that would become x1, and we would go around this loop again and again until we reached a point where we had x star is equal to g of x star, and we called that a fixed point, and we said we'd converge to a solution. All right, and this was a way of solving, solve nonlinear equations. Solve nonlinear equations. All right, and that's a very useful way. Newton's method in particular is a nice way. And what we saw in the last lecture was if we wanted to do multi-dimensional equations, I said, well, we're going to learn how to use scipy's techniques to solve multi-dimensional equations. And so we learned about scipy and some of the power for doing both single and multiple, or systems. Multiple nonlinear equations. Oops, having problems writing today. All right, so another approach that we're going to talk about today uses what are called optimization methods. Okay, and the basic idea is as follows. So I'm going to draw a little graph here. So suppose I wanted to find the roots of something really simple. Suppose I wanted to find the roots of f of x is equal to x minus 1 equals 0. Right? So that's kind of a silly example, right? I can obviously just solve for that, but it'll make the point here. So let me draw that on the paper here, if I can get a hand straight enough to do that. Okay, so in f of x equals 1, or x minus 1, this will be my point 1. So I'll have some line that will go through there. All right, and so my root is right there. Presumably, we'll make it nice and big. Okay, that's my root right there. All right, so one way, right, was to use Newton's method, which would predict a line and it would iterate to that point where we find the root. Another way would be to take this here, to take our residual, right? So this was, in residual form. So if I make an incorrect guess, that gives me something that's not equal to 0, which is my residual. And the other idea is to say, well, let me define something I'm going to call s of x, which is going to be my f of x quantity squared. Okay, which in this case would be x minus 1 squared. Right? And you might say, well, why would I want to do that? Well, what I would do now is instead of having a line, I'm going to turn the area around my root, and again, I'm going to have to try and draw computers. instead of having something that crosses over from positive to negative, I'm going to now have something man, this is not good. I'll start here. How about that? That's better. I'm going to now have a parabola, right? Or something that's convex. And the nice thing about that is if I can start here, I can work my way downhill, okay, until I minimize. So now I've turned a problem from root finding over here, where I'm trying to look where it crosses from positive to negative, or from negative to positive. And over here, I'm doing minimization, okay, where I'm trying to find from big to small. All right, and it turns out that this switch from root finding to minimization allows me to use a whole bunch of different kinds of methods. All right, we're not going to, unfortunately, have time to talk about all of these methods, but I want you to know about this basic idea, about the difference between root finding and minimization or optimization. Okay, you can think about minimizing, or you can think about maximizing, right? So optimization, we often think about maximizing something coming to the top, but it turns out that's the same thing. All I have to do is flip this upside down if I want. I could put a minus sign and that would make it a max. And minimizing is a pretty easy way to do this. Okay, so this function here, the square of our residual, this has a name in optimization techniques, and this is called an objective function. And the hope is that your objective function has some nice convexity to it, which will allow you to do this optimization. Sometimes it's also called a cost function, because you can think of this as, your low cost, and then everything else here is high cost. And again, there are many methods to do this, but unfortunately for us, for today's lecture, we just don't have time. So no time to learn the methods, which is a bummer. So I'll put a frowny face. Okay? But there are many great places to learn this, and I'd highly recommend that you check out my colleague John Hedegren. He has courses on this. He has online materials on this, and he's an optimization guy, and so I highly recommend you check him out if you're interested more in methods. Okay, so that's our brief introduction to optimization. So we are now going to turn to a couple of examples of optimization. The first will be optimization in Excel. And that is going to use what's often called solver in Excel. So, I'm really just going to do an example and then pause for an activity here. So I'm going to just put that on my notes here, and we're going to turn the system here over for a second to that guy. So let me grab a picture of me. Oh, went one too far. There we go. All right, so here we are in Excel, and here is the example that we are going to do. We would like to find the roots of this cubic equation, x cubed minus 10 times x minus 1 squared is equal to minus 1. All right, so we'd like to find that, and here it is, a plot of it here. I made a column of values of x and a column of values of f of x. You'll notice that this has been changed into the residual form. So the same that we had to do for root finding, it's also very valuable to write things in the residual form, because we're going to want to have a cost function that we can minimize, and so we're going to also square this f of x to be our cost function, and so we want that to be equal to 0. So I have this equation here in residual form typed in here, so x cubed minus 10 x minus 1 squared plus 1. All right, so the minus 1 comes over and I get plus 1. Okay, and I just make a little plot of that so that we can see where the different roots are. All right, so to find these roots, we're going to need to use a tool in Excel called Solver. And to get at Solver, if you're on a Windows machine, you come over to File, and you come all the way down here to Options. You click on Options, and it'll bring up this menu. And you need to click on Add-ins. And down here at the bottom in this list, if it has inactive, mine I've turned it on, but it'll have Solver add-in. So you click on Manage Excel Add-ins and click Go, and then you'll need to click that box so it has a check in it. Solver add-in, check. You click OK. All right. If you are on a Macintosh, there is a similar menu. I think it's in Tools, and then you'll see Add-ins again, and you'll need to click Solver add-in and click OK. All right. So that for the Mac, I don't have a Mac virtual machine here, but it will be Tools menu, Add-ins, and then Solver add-in. All right. And once you've done that, then you need to find. Oh, excuse me. You might be on the Home tab. You need to click on the Data tab up on the ribbon, and all the way on the right-hand side there will be Solver. So you click on Solver, and it'll bring up this menu, and it's going to ask you for an objective, which is where you need to put the objective function. So before you can do that, you need to define an objective function, and I usually like to use a table like this. And what you're going to need to do is have an initial x value, which is going to be your guess. Then you can define your function in residual form, and then you define your objective function as the square of that function in residual form. So here I just have x, it's a value I'll type in. So suppose my initial guess is at 2. Okay, then my function, I will type in the same thing that I typed in all these other places, right? X cubed minus 10 times x minus 1 squared plus 1. And that should be 0 if I have the right answer. So you can see it should be a little less than 2. So if I do 1.9, for instance, I get a smaller value, 1.8. I don't know if that was small or not. Crossed. So it's somewhere between 1.8 and 1.9. I would guess is where the answer is going to be based on what my residual did. And the objective function here is the square of the residual, which is just that C35, that one right next to it, squared. Okay. Now sometimes people call the objective function the sum of the squared error for a reason that we'll see in the next example. It'll be a sum. You can see why it might be called the squared error, right, or the square of the residual. This is the sum of the squared error, and that will happen when we have multiple equations, which we'll see in the next slide, or in the next example. Okay, so now how do we go about and do this? Notice this is just an image I put here for the example, but we come over to Solver. Okay, you click on the objective, so you need the objective function, so you click there on the sum of the squared error or on the objective function. And then you need to set the objective to either a maximum, a minimum, or a certain value. You can do minimum or value of 0. I usually like to do minimum because then it says it converged. If you pick value of 0 and it tries to find a minimum, then it might tell you, oh, I never converged, pardon me. Okay, and then it says by changing which variable cells. Well, in that case, that's x. We want to change x to change what our objective function is. And then you can add constraints. So for instance, you can click to make that value greater than or equal to 0. All right, and that would try and constrain the search to only positive values. Right. A lot of times constraints make the optimization harder. So I'm just going to delete that constraint, but I think you get the general idea. All right, so then I come down here and I click Solve. When I click Solve, it gives me some results. It says Solver has converged to the current solution. All constraints are satisfied. And I click OK. And notice that it changed this value for me. All right, it varied it. It was indeed between 1.8 and 1.9. It found that the residual is 2 times 10 to the minus 6, so that's pretty good. And the sum of the squared error, or the objective function, is down near machine precision. All right, so it found a root there at 1.86. If I wanted to find a different root, say out here at, I don't know, 7.5, I can try that guy. All right, and I come up here to solver. I run the same thing. Notice that there's methods here that you can pick between different types of optimization schemes. You can go read about those on your own time or in Dr. Hennegren's materials. Anyway, click on solve. Now it found 7.49 and it's doing a pretty good job there. Okay, so that's how you solve a simple optimization problem to find roots. Here's an activity here that I'll give you a head start on. There's a key here if you get stuck, but I'll give you a head start on this guy. So this is now 2 equations and 2 unknowns. So how are we going to go about doing this one? Well, in this case, you're going to have 2 values, an x value and a y value. I call them x1 and x2. Perhaps that's a little bit confusing. Maybe we can go through and change that here. This one can just be x, y, x, y. All right, and this one can be x, y, x, y. All right, and if you think about this over here is my x, and this one is y. Oops. All right, so what I'm saying is I have 2 functions, and the intersection of these functions is where my solutions should be. So suppose I pick over here, I want to say, and these are just coming from these here to plot them. Suppose I want to find this solution here. So over at around 1/2 in x and somewhere around 5 in y. So 1/2 in x, 5 in y. And I need to then put in the functions. So these functions need to be in residual form. So this is going to be x squared plus 3 times x plus 2 minus y equals 0. And then function 2 is 2 times x plus 3 minus y equals 0. All right? And then now I'm going to say, well, what is the error from the first one squared? So that's the residual squared. Then I'll say, what's the residual? That's the residual for the second equation. And I'll put, in this case, I'll put a squared value. And then my total objective function is going to be the sum of those squares. Oops, and I messed up the formula. But let me try that one more time. Equals sum of the squared error. And that's why I have a sum of a squared error. All right. And now I can go up to solver and set my objective to be that objective function. And note that when I change cells, it allows me to select both cells. So I can change 2 cells and run solve. And it says it's converged. Okay. And it found a solution at 0.6 and 4.2, and I can see that from my residual, it has indeed converged to a solution. All right, so I walked you through the solution there. This one has the same thing. Note that what I was doing in the previous one over here with this x1 and x2 is I can rewrite this in a vector format. All right, so I can take y equals x squared plus 3x minus 2 and rewrite that as a vector function f of x equals 0, where I have f1 of x1, x2, etc. And I can rewrite this as x1 minus x2, in this way without using x and y. And that will be valuable for us when we think about our Python solution here in just a second. All right, so that's it for the optimization in Excel using solver. So let me come pull this guy back up here, and we're going to come now over to 3 and talk about optimization in Python. Okay. And in Python, we are going to use scipy.optimize, just like we did in the previous lecture, scipy.optimize. But we're going to use a new function called minimize. All right. And I think the best way to do this is by also doing an example and an activity. So I'm going to work my way over there to look at this example. So let me pull that up right here. So here is the optimization example in Python. So as is always the case in Python, or typical, I have my boilerplate at the top. I need to import NumPy, and I'm going to import the plotting tools, and I'm going to import scipy.optimize as opt, as opt, so that I don't have to keep typing optimize everywhere. All right, so how do I solve a single equation? It's actually very similar to solving something with root, optimize.root. What I need to do is I need to define an equation that is in residual form. So in this case, x squared plus x minus 5. And I define that as a residual. And then instead of defining the function, I define the objective function, which I'm calling here s. And I return the residual squared. So I need to return not just the residual, but the residual squared, which is now my objective function. All right, and so that's what I'm saying here. So you need to first put the equation in residual form and then define it, squared. And then here's some stuff to make a plot. And then just like with root, like we did last time, I need to define a guess value, and I call opt.minimize, and I give it the first argument is the function name, all right, and the second argument is the guess. And then it also returns a dictionary, so I need to do .x to return the value of the solution instead of a whole other bunch of junk that opt.minimize returns. All right, so this will then print example. It will print x, and it will print the objective function and put that up on the plot. So let's run that and see what happens. Okay, and you can see here it actually plotted the objective function for me. And so note that that objective function isn't the same thing as x squared plus x minus 5. It's actually giving us something that looks quartic, right? And my solution there is at the bottom, all right? And you can see that the objective function has indeed found a minimum, and so it's at 10 to the minus 15, very close to 0. Okay? Oh, pardon me. I don't know why I got the yawns all of a sudden. All right. So the last thing to look at is what do we have if we have systems of equations. So recall in systems of equations, I have systems, a bunch of equations in this vector format, and now if they're all in residual form, they all equal 0. All right. So this is the same as we did last time using root. And if you look here, the main difference, I guess I'll talk through steps. So the first step is to import the module. The second step is to write your equation as given in residual form, in vector form as well. Okay, and then you need to define a Python function where you have a line for each function, for each of the residual functions in residual form. And then finally, you'll add up all of the residuals and square them all and sum them up to make a sum of a squared error and return that sum of the squared error. So just like before, the function that you're defining is the objective function, and so it returns just a scalar value. This is different from the root, where root returned a vector with all of the different values of the residuals. All right. So finally, then, to call the function, you need to set an initial guess. That guess is a vector of all of the different arguments, x0, x1, etc. And then you call the minimize function opt.minimize with the name of the objective function and the guess. So let's see the example of how this is done. So suppose I want to solve this equation, y plus 2z equals 0, and sine of y over z equals 0. And in our standard pardon me. Their standard notation, I would convert y into x0, the x component 0, and z into x1. So this is converted there. And so now I can write down the different functions. f0 is x0 plus 2 times x1. f1 is sine of x0 divided by x1, the same as here. And now I define sum of the squared error, which is the square of each of those residuals summed up. And I return that. So notice that's different from root. For root, I would have defined numpy.array with f of 0, f1. Okay? So, but for minimize, I'm going to do the sum of the squared error. All right? So then I give it a guess. Again, the guess needs to be in an array because these are array values. They're calling the different values there. The size of this array needs to correspond to the size here. And then I call opt.minimize, give it my objective function, give it my guess.x, and this will be the second example, and we'll see what's going on there. All right, so that does return an example. All right, so there's a couple of practice problems that you can do here. The first practice problem is to go back and try and use this one to find a different root. The second practice problem is you can solve this different equation. I think this is a great practice problem to spend, if we're in class here, to spend the balance of the time in class on. You can also practice in Excel. Make sure you can follow through the steps in the solver format that I had for you. All right, so that's all I have on optimization, and I hope this is helpful for you and that you'll be able to continue and use these tools. Have a great one.